Math 2415, Calculus 3, Curl and Divergence, Section 13.5, Curl and Divergence, Video 6 of 6. In this last video, I just want to make some connections to Green's theorem by showing you some alternate forms of Green's theorem in terms of both curl and divergence. So far, we've seen two forms of Green's theorem. The original one said that if you find the line integral over a curve of p dx plus q dy, where p and q are functions of x and y, then that was equal to the double integral over d. And by the way, this was a closed curve, so we could do this. Then we could find the double integral over the region d bounded by the curve c of the partial of q with respect to x minus the partial of p with respect to y dA. We also looked at it from vector form by rewriting this as a dot product and observing that p comma q was just the original vector field and that dx dy was really just the derivative of the position vector, and concluded that the line integral over a closed curve c of f dot dr is equal to the double integral over the region d of the same integrand as before. And remember, as a consequence of this, if the vector field was conservative, then this difference was equal to 0, and hence the integral was equal to 0. But now we have two new forms. One form is in terms of curl. And the curl of f. I kind of foreshadowed this previously when we first introduced the formula for curl and pointed out that the third component of the definition of curl was this difference. Partial q with respect to x, partial p with respect to y, minus partial p with respect to y. Well, what does that mean in terms of curl? Well, if we start with the same line integral of f dot dr over a closed curve, then we can set up a double integral, still dA, but this being the third component or the k component of the curl is just the curl of f dot k. Because think about it, k is the vector 0, 0, 1, so if we form its dot product with the curl, the first two components of the curl would disappear, and you'd be left with just the third one, which is this. So that's nice, because if we're setting up a double integral of this form, we can just use a line integral, and vice versa. But you can also write it in terms of divergence. Now, writing it in terms of the divergence is a little trickier to just look at and go clearly. So I'm going to show it to you, but if you really want to see the details that take us from here to a double integral in terms of divergence, I invite you to read page 794. In the middle, there's a box that says 12, and it says this version of Green's theorem in terms of the curl. And then it goes through all the algebra and calculus that takes us to the last one, which is, if you're finding, plus there's another subtle difference. If you're finding a line integral over a closed curve, some people call it a contour integral. But instead of f dot dr, it's f dot n, so a normal vector, and I believe normal unit vector? Yes, normal unit vector. And instead of dr, it's ds, so you're integrating with respect to the arc length parameter, so it's a different setup. Then that's equal to the double integral over the region d of the divergence of f dA. And again, it's a little bit more of a transition from the curl version to this version because the line integral is also represented differently. I think the transition from the first vector form of Green's theorem to this one is pretty obvious because this was just the k component of the curl. But I invite you to read on page 794 if you want to see the transition from double integral in terms of curl to double integral in terms of divergence. I wish I could speak more competently about the physical implications of Green's theorem in terms of curl and divergence, but not being a physicist or engineer myself, I would just be floundering around. I would ask somebody who knows more about physics and engineering than I do until I do my research and can speak more competently on it. Alrighty. Yay, another short video.